some key points immediately to take on board from this image is that you can see the shadows here underneath the platform, which means it's not being cut off. We are actually seeing the water underneath the platform legs, so there's no possibility of that being cut off by some horizon. Yes, so there is the apparent horizon there. That is the horizon what Globers call the apparent horizon. It's the horizon where the sky meets, sort of, it's a bit blurry, sky meets the water, and you can see that is above and behind these platforms. So key points of this thing is the horizon's there. We are seeing where the legs meet the water. There's nothing being obscured. There's only one horizon. That's the apparent horizon.
They also have a horizon directly behind the actual claim of Earth curve obstruction in the near foreground, despite the fact that the horizon that should be obscuring it is actually behind it. So this is a rather excellent capture of a black swan.
Absolutely ridiculous for any any flatty to go on about the geometric horizon when we are saying the geometric horizon. So here you can see here the geometric horizon has no special visual properties at all anymore. There's nothing special about it whatsoever. There's nothing it does of interest to you. And you can see here the horizon has jumped up, raised up, or loomed up in this case because you've got extreme refraction. To this position. So this is what you would actually see, and indeed there are videos from flat earthers who out of Sydney are looking outside their window and seeing the horizon move up on different days by different amounts caused by refraction. Flatties claim that the horizon has never moved up as a result of refraction or looming. They say that just doesn't happen. Well, we've actually got a flatty taking videos out there. In fact, Roohif put me onto this actually, of this Australian in Sydney who's taking videos seeing the horizon go up and down.
In certain weather conditions, you get different variations in the actual water levels against the towers, the permanent markers, and the headland. Okay, I'll just show you a couple of things. So there's one day, just randomly going through, on the 9th of the 10th, the visibility for the horizon was there. When we get things like this, when we get the water at the top of this tower. Now, the highest I've ever seen the Pacific Ocean against the tower is there, right there. Okay, the lowest I've seen it on a clear day is around about there. Okay, so we're getting this movement in the actual ocean, but is it movement in the ocean, or is it clearer visibility? Or is there something happening to this section of ocean that allows me to see further into it?
in perspective on a flat plane with an elevation of 1 foot, the image that we are looking at, that is this Black Swan image, is impossible on a flat plane. Because if I change the curvature on this planet little thing to 0, this is what we would expect to see. Now, the important thing here is because we are at 1 foot, or even if it's 1.5 foot elevation, because of the distance and the acuteness of angles, the difference in our vertical between the bases of these towers is insignificant, yet we see quite a significance. Now, we know we're not looking down. We know it's a very low acute angle. So the only thing that I can do now is say we'll have a negative effect, and this is what I've had to do, which is a negative 0.0 concave Earth to actually produce that image, which is why I support what Glenn just said, Roohif, when he said it's over a K value of 1. It absolutely is, because the estimated vertical difference between the bases of those two, and we just have to assume the following: those bases intersect the same water, and that water is level, and that's it. That's all we have to assume on that side, and then we say, well, we are above the water. Now,
yes, because effectively, sorry to interrupt, but what you're effectively saying is that these are at the camera's level, the base here and the base here at camera's level, and we talk about the perspective causing things to get smaller around your center of vision, but our center of vision, our eye line, is actually at next to nothing, almost at water level. So in other words, these two things should line up at their bases, and because we can see the bases and they're not lined up, therefore we cannot be on.
However, the one caveat here is to produce this image on a flat Earth. We could do it, but the camera elevation would have to be probably about 60 foot.
Right. But we know it's not, yeah. And also, actually, what you were talking about, convex rays, yes, Philip and I actually modelled how you would get the impression of being on a flat Earth. What you'd have to do on a flat Earth to give you the results that we see for a spherical Earth. And it turns out, as you correctly pointed out about the convex rays, you'd have to have convex rays, and what's more, than to maintain that temperature gradient, you would actually have to get less than absolute zero, just a few kilometers up in the sky. So it doesn't work